Hey everyone, welcome back. So from this video, I am starting a new series where we'll try to understand the math behind machine learning, and not just understand, we'll also implement the mathematical concepts, the important ones. So what is the purpose of this playlist? So instead of just memorizing the formulas, what we are going to do is we are going to understand why, for example, this matrix vector dot product operation matters and how it works at a practical level. Right. So by the end of this video, you'll not only understand the implementation, but also why this operation is so powerful in data science applications. Now, to demonstrate the understanding of math and implementation, I'm gonna use this platform DeepML. Now, this platform is basically Leetcode for data science and ML. So, it's an interesting platform, and we are gonna solve the problems mentioned here. Okay. So, we'll start with the first one, matrix vector dot product. All right. So, let's just start. Okay, so before we just directly go into the implementation, which is frankly very easy because you all would have studied this matrix vector dot product in your plus 2 or even in your 10th. So we are not going to do that. We are going to first understand the real world context, right? So where this matrix vector multiplication or matrix vector dot product is used. So let's try to understand that. Okay, now where is this used? Firstly, what do I expect from you if you are watching this playlist? I don't expect much, but a little knowledge about ML helps, right? Because I'm not gonna explain you every nitty gritty of ML, but if you have some hands-on experience with ML, okay, I don't expect any math knowledge from you, except the 10th standard mathematics, okay, and 10th standard also very dumb level, okay. So let's start, okay. In neural networks, you have to multiply like time and again. What you usually do is we have to multiply this weight matrix with the input matrix. Okay, if you don't know, fine, no need to understand that, but I'm just trying to give you some real world context here. Now, when you have recommendation systems, we usually multiply this user preferences, which is a matrix, no, user preferences, which is a vector, with the item features, right? So movie features or something, which is a matrix. Okay. In natural language processing, we usually project word vectors. Now, if all of this sounds confusing to you, don't worry. When you will actually do some ML, you'll get to know. But I'm just trying to build some grounding here, some real world context here. Okay, so let's just take a practical example here. Let's say we have movie ratings represented as features like this: action, comedy, drama, and romance. Okay, so a movie is represented by these four features: action, comedy, drama, romance. So a movie one can look like this: 0.8, 0.3, 0.1, 0.0. So how do you interpret this number? The way you interpret this number is for action, the value is 0.8. It means this movie has a lot of action. 0.3 comedy, so it has some amount of comedy and very less amount of drama and no romance. So this is actually a action movie. That's what it. That's how you interpret these values. For movie 2, let's say we have 0.2, 0.7, 0.2, 0.4. So what it says is this movie has a lot of comedy because 0.7 the highest value, and some amount of romance. So this is sort of a dramedy movie, right? Drama and romance, like romantic comedy. That's what it's a rom-com basically. And we have a user preference, right? Let's say we have a user preference array, and these users preference are, let's say, 0.9, 0.6, 0.2, 0.3. So how do you interpret these values? This guy prefers action movies. Then after that, he prefers comedy movies. He doesn't prefer that much amount of drama or romance movies, right? So that's why I put 0.2, 0.3. Now, where does matrix vector multiplication come into picture? The way it comes into picture is you create a matrix of these two guys, and if you do a dot product or multiply it with this user preference vector, what you get is you will get a new vector which will give you user preferences for a movie. That is how likely it is that this user is gonna watch this movie 1, or how likely is it gonna be that this user is gonna watch movie 2. Don't worry, I'll take a step-by-step example which you'll understand it better way, but that's how it is used. Like if you want to recommend a movie to a user, you take a matrix of item features and multiply it with a user preference to finally get score for each movie, right, based on how well it matches our user preferences. Fine. Let's understand now this at a very conceptual level. So what do you mean when you do a dot product? Now I think you're already aware with a vector dot product. So if you have two vectors, let's say v1 and v2, what does this dot product between two vectors mean? It simply checks. So if you have a vector in space like this, when you do a dot product, that is simply pairwise multiply the elements of this vector and add them up. You are checking how much these two vectors aligned with each other, right? For example, if you have two vectors like this, dot product will be high, showing that these two vectors are aligning a lot well with each other. But if you have two vectors like this, which are perpendicular to each other, then in this case they are not aligning well, so your answer will be 0. But we are concerning about matrix vector dot product right now. So what we are doing essentially is, when you are doing a matrix vector dot product, so let's say you have matrix like this, A, B, C, D, and you have a vector like this. For matrix like this and you have a vector like this, let's say we call this values as v1 and v2. What we are essentially doing is we are taking each row of the matrix as a separate vector, and we are finding out how much our input vector aligns with each row, right? And we are going to create a new vector. We are going to create a new vector which represent this alignment scores. So let's take an example. Okay, so let's say we have a matrix A which has 1 2 1 2 2 4 values. Okay, so this is our matrix, and we have a vector B which has 1 2. So what you are essentially doing is, so what you can see is, you can see this matrix A as row 1, which is 1 2, and row 2, which is 2 4. So you can think of this matrix as two separate vectors represented by row 1 and row 2. And for each of these rows, what you are doing is you are checking its alignment with this vector B, right? So let's just call this guy as B, this vector B, for which you have to do matrix vector multiplication. For each row, you are trying to check its alignment with vector B using the dot product formula. So if you want to see the formula here, the formula is pretty simple, guys. So the output vector here, C, let's just call A B equals to C. The formula for this C will be actually like this. The formula is pretty simple. So if you have A matrix, you have B vector, then formula for Ci, that is for a given value of C, you have summation of A I j into bj for j belongs to 0 to n minus 1, right? So essentially what you're doing is, to get a so equals to, it will have two values. So this value is actually equal to first row multiplied by first row's dot product with the entire vector, right? So first row's dot product with the entire vector, and this guy will be second row's dot product with this vector, right? So that's what this formula is saying, right? So you can pause for a bit and satisfy yourself that this is exactly what this formula does. So in plain English, for each row in matrix A, multiply each element with corresponding element in vector B and sum up all these products. Simple. Now let's just walk you through this example. So we had two vectors here, which is like matrix here 1 2. What is it? 1 2 2 4, and we were doing a dot product with 1 2. Okay, fine. So let's just do it. For row 1, take the first row and multiply it, take a dot product with the first vector, with the vector. So it will be 1 into 1 plus 2 into 2, which is 1 plus 4 equals to 5. For row 2, on the same grounds, it will be, take the second row, 2 into 1 plus 4 into 2 equals to 2 plus 8 equals to 10. So your answer is simply 5 10, the resultant vector, right? Now one important thing here is obviously that if this guy is m into n, this guy has to be n into 1. That is, the number of columns in this matrix has to be equal to number of rows in this vector. Otherwise you won't be able to do the matrix vector dot product, right? So let's just try to implement this. I guess the concept is clear. I also gave you one practical example of how this works, so I think this should make sense to you. Now let's just implement it. Okay, let's try to implement this now. So we are given this matrix A and a vector B. Okay, so first things first, what I'll check is, like, frankly it's not required, but let's say if matrix A is not existing, basically the matrix is empty, we can return -1. Although I don't think that will be the case here, but just for safety here. Now what I'll get is, I'll get the dimensions here. Okay, so I'll just get the dimensions here. The first, let's get number of rows in A. Okay, so these are rows in A. Then I'll get number of columns in A. Okay, it will be length of A of 0, right, because A is a list of list. So length of A of 0 will be number of columns in A. Pretty simple. And let's just get the number of elements in B, right? So it is simply the length of vector. Length of vector, you can say number of rows in B, if that makes sense, because what has to happen is this n has to be equal to O. So that I'll write here, if O is not equal to n, then we have to return -1. So these are incompatible, right? This multiplication, this product, this matrix vector dot product is incompatible. So that's what we are going to do here. Otherwise, let's just compute the dot product. Let's just compute dot product for each row. That's exactly what we have to do, right? For each row, we have to compute its dot product with respect to the vector. So I'm gonna go for I in range m. For each of the row in A, result of I. So first I have to define result somewhere, right? So what is the size of result, by the way, guys? So if you want to see here, what is the size of result? If matrix size is m into n and vector size is n, then your result size is m into 1, right? So for each row you're going to multiply with the vector. So if you have as many rows, that will be the size of the vector. So what I'm trying to say here is, if you have 3 rows, R1, R2, R3, and let's say this was some 3 into 2, and your vector size here is 2 into 1, right? Because this has to match, right? So number of columns here has to match the size of vector. So the output size will be what? 3 into 1, right? 3 basically, right? So with that settled, let's define a result array, or basically result vector. Let's initialize result vector. So the result vector is simply right now 0 into n, right? 0 into m. Fine. Okay. So result of I will be actually equal to what? You have to do a summation. We already discussed, right? Summation of what? ai j into bj for j in range n. This is essentially what I'm doing is I'm calculating the dot product of ith row of A with the vector. That's essentially what I'm doing here, right? Where I'm just doing a dot product of each row with the vector, and finally we can just return the result, right? If everything is correct here, this should run. And indeed everything is correct, so all the test cases are passing. Okay, so the question is done and dusted there, but I want to also talk about some optimization and efficiency, because this is not your regular analytical implementation video. I also want to talk about how you are going to do this matrix vector dot product at a practical level. So in practical level, you are actually not going to use this list of lists and lists. What you are actually going to use is, you are going to use NumPy here, right? So you will actually use NumPy. And instead of just directly operating on lists, what you're going to do is you're going to create a NumPy arrays of it, right? So you will convert that list of list into a NumPy matrix like this, and b of np equals to np.array of p. So this effectively is a 2D NumPy array or matrix, 2D NumPy array, and this effectively is a 1D NumPy array, right? That's what it is. And we'll have also check for compatibility here, right? check compatibility. So that is very simple. You will have to do a numpy dot shape of 1, the number of columns in A. If it is not equal to bnp of shape of 0, that is number of like the length of this vector b, then you'll have to return -1. Okay. Otherwise, your answer is simply, frankly, NumPy, it's very simple. You just have to write a.np at the rate bnp. Okay, if they're compatible, then this thing will compute the matrix vector dot product. So you're not going to actually use the for loop and all, because the benefit of writing this is this operation is actually implemented in C. Okay, so if you don't know, Python is a terribly slow language. So we usually don't write this mathematical operations in Python because they're terribly slow. Instead, we delegate this task to internal C implementation. No surprise there. These libraries are written in C because C is very efficient, because it uses something called as a SIMD instruction, like single instruction multiple data instruction. So it's a fancy word for operating multiple values of your array or vector at the same time. It is simply optimized for memory access patterns. That's why this is used. So let me just run it and see if this works. And indeed this works as well, because we have just simplified the code, and this is also very optimized. Okay. And coming back to our recommendation example, so what you effectively do here is you will do a matrix vector dot product between the items, like the movie features and user preferences, and you'll get scores for each movie, right? So you can verify it for yourself now, because I've already taught you the entire concept and implementation. And finally, once you have got these scores, the final score vector, we can just sort them, right? We can just sort them and return these scores, and we can use these scores for post-processing, showing the users the movies, right? Now, in conclusion, what you understand what a matrix vector dot product is, we have implemented it. We have also seen why it is so fundamental to machine learning algorithms using this example. And you also know how to think about this operation beyond just the formulas, right? And yeah, I guess that's that. And let's see what next problem we solve. So if you enjoyed this explanation, hit the like and subscribe for more videos in which I'll break down this machine learning concepts at a practical level. And if you have any questions, do drop a comment, and please let me know if you have any specific topics to be discussed. Fine, I'll see you in the next one.